Rigid body dynamics goes by the acronym RBD, pertains to any rigid body that is dynamically being simulated in Houdini, right? Makes sense. And that pertains to all sorts of things. I mean, on the top level, the most simple version would be like this ball. If I want this ball to be a rigid, unbending object and to simulate it going down these stairs, well, that is an RBD simulation, right? We're simulating the forces that are affecting this ball frame after frame. The same is true of this example, the cube break. We have a cube that has been cut up into a bunch of different rigid body pieces, and these pieces do not change shape at all. But upon the simulation, they are all free to move independently, right? This is where we get that rigid body destruction from. It's a single bouncing ball. It's a dominoes knock-on effect. It's a building collapsing. There's so many different applications for rigid body destruction, and that is kind of what we're going to explore here. Now, in its simplest form, I figure we can just build one from the ground up. This will be our first RBD simulation. So we'll create a geometry node. I'll get rid of these guys, and we'll just call this squab test. The reason I call it squab test is because we have our test geometry squab right here. This monstrosity. I think this is a real animal. I certainly hope it's not. Really upsetting to look at this. But I figure this is a good illustration. Rigid body simulation is different than, all the other simulation types because of the engine that is used to run it, right? It is called the bullet solver. And we'll kind of set this up and make sense of it as we go, but we have our object that we want to create. And then I think I will go ahead and just transform it up on the y-axis a little bit. I'll turn on my grid too so I can kind of see that. And with that squab where it is, I kind of just want to drop it down onto the ground, right? Simulate it, basically. And so what we'll do is we'll make another dot network, just as we have before. And let's actually make a little null here too. I'll call this out squab. And I will reference this SOP path in the actual simulation itself. And in this .NET, we kind of want our usual suspects, right? The first thing we want is a gravity force, right? We want to be pulling these things down based on Earth's gravity here. We want our merge node, in which we plug in our ground plane, right? That infinite collision geometry. And we want our solver, right? Our solver and our object, in particular, the brain and the notebook with all the information in it for the Brainiac. But of course, this is not a pop simulation, not really. This is a rigid body simulation. I say not really, it's a bit of a teaser. I'll explain that later. But we want a specific solver for the task at hand. And that is the rigid body solver. Makes sense, right? So we plug this in. And then, of course, we need to load in our initial geometry. In our case, we're not sourcing in geometry every single frame. We have a single squab that I want to load in and simply drop to the ground. So what I do is I make a RBD object node, port it in, and then by default, we've got a little default sphere here that it's loading in for us. We can see the SOP path is populating there. But we can, of course, just replace this with the path to our squab. And now, for all intents and purposes, we kind of have our first simulation. I mean, not to brag or anything, but that was pretty fast, huh? So if we hit play here, we'll notice our squab is kind of doing its thing. That's pretty cool. Now, I mentioned the bullet solver engine earlier, and bullet's really a good name for it because it was designed for speed. Now, bullet in particular is used only with RBD simulations. Pop, vellum, flip fluids, all the other stuff uses other methods. Bullet was designed specifically for rigid body simulation. And it's, all in the algorithm math under the hood that doesn't really matter to us. The point is, it was built for speed. And the way that it achieves that speed is by approximating collision in the most lightweight way possible. And the way that it works is it takes your incoming rigid body object and wraps it, almost shrink wraps it in a way, in a proxy geometry, right, that we can actually visualize ourselves. We can see this if we go to the RBD object, and in the collisions tab in the bullet data tab, we can scroll down and say show guide geometry. And look at this. This is really what is being simulated. Like, we are visualizing this for all intents and purposes, But this is the thing that is actually being used for all the collision data. And you can see how much more lightweight it actually is. These giant swaths of single polygons that are super duper lightweight in shape. And that is what is approximating all this that would obviously take a lot longer to calculate if it was all being accounted for. This is the power of the bullet solver, really. So if I hit play, we'll see that's actually the thing that's working, right? That is what is a convex hull, right? It's all the convex portions of the geometry. You can think of convex and concave. I'm sure I said that in the weirdest way possible. Concave. And thanks to the power of Google, I can just Google this thing. This is the difference. Concave is anything that basically goes inwards. I mean, like a cave, right? And convex is anything that goes outwards. So what this is doing is it is generating a convex hull around the object with no concavity at all. That concavity requires additional, polygonal definition and whatnot to calculate, and therefore makes it a whole lot harder to do. The simplest and most efficient form for rigid bodies to be simulated is wrapped in a convex hull with no concavity allowed. Makes the math a lot lighter under the hood, which makes everything a lot faster. And if we turn on the display geometry 2 and we enter wireframe mode, we can see how it's working. It's basically kind of taking the max, kind of like we were doing with the bound node, where it was drawing a bounding box around it. Well, instead of drawing a giant box, it's trying to draw a little more of an accurate shape. But it's kind of a hybrid between the two, right? It's original source geometry and a bounding box around the entire thing. And so what we get is a finished simulation that looks like this was simulated, but in actuality, it was using this proxy instead. Right? We can see kind of how that's wobbling and rolling according to this actual shape. So that's pretty cool. But as I'm sure you can imagine, if we really needed the information from the concavity, right? Let's say, I'll turn this off, exit wireframe mode. Let's say we were doing a simulation where we had a whole bunch of rigid body balls, for whatever reason, shooting at this thing, and we wanted it to hit him in the chest or something where there is concavity, right? We wanted accurate contact with the actual shape of the object. Well, that is where we would need to start amending the overall approach to simulating this thing, which unfortunately does strip some of the advantages of the bullet solver. The bullet solver is designed to run on convex approximations of your geometry, but you are not tethered to that, because obviously we all need a little flexibility in our lives, you know what I mean? Sometimes we just gotta go out to that party, Mom, no matter how late it is, and even if it's on a school night. Sheesh. I'm over 30. That's not appropriate. Even if it's not optimal, if we need it, we can do it by changing the geometry representation, right? We have our convex hull, but we can very easily change this to concave, introducing all that concavity back in. Now we don't even see it because it is so accurate to our surface that it is perfectly in line with our display geometry now. And this will still simulate nice and fast because it is one object. Even though this is playing back fast, typically using concave approaches to the simulation kind of flies in the face of the point of it. So you kind of want to stay convex if you can. But there's also other simplified geometry types that you can use if you want to instead. Like we have the convex hull here, and I push play, and it wobbles a little bit when it lands, right? But if I want this to just land, I can use a box instead. Now this is actually a traditional bound now that we were using earlier. And in this way, when it settles, I mean, it really settles, It doesn't wobble like it was doing before. And so now when the squab lands, it basically is tethered to the motion of that box. So in looking at rigid body dynamic simulations, we are now aware that it uses the bullet solver engine to approximate collision geometry to be as lightweight and fast as possible in order to simulate these objects that, again, are not supposed to deform in any way, shape, or form during the simulation. They are rigid bodies. It's cool, it's optimal, it's hyper flexible. It can be used for single objects being simulated, or for multitudes of objects, copies of objects, fractured pieces of objects being simulated. But there is some nuance in that statement, and that's what we're going to explore next.